screen recording. Yep. So least squares regression line is the line that makes the sum of the squared residuals as small as possible. That's fancy talk for it does a lot of math behind the scenes that we are not capable of handling. Even myself, I would not want to have to find the actual square of all the residuals in that situation. So that's what the least squares regression line is. We'll just use the apples to click that button, and it will tell us it's the same line that we did last time. It's called the least squares regression line. You might see it abbreviated like this, LSRL, least squared residual line. And here's our first one that kind of tells us it. It's measuring somebody's foot length in centimeters, because most of the world works in the metric system, and how tall they are. They're seeing if there's like a relationship between how big somebody's foot is and their height, which there probably is. You know, the bigger the foot, the taller the person, but not every time. So what they did is they measured 6 different high school students. So not a very big sample size. But they did that, they put it into the applet, and they got the least squares regression line of this. It's got a y-intercept of 82 and a slope of that. It says use the equation to predict. So anytime we use predict, we take the number that they gave us and put them into the equation. We'll be putting them in for either x or y. So let's see who this 32 is. 32 is the centimeters of the foot. And isn't that what x stands for in that situation? X is the centimeters of the foot in centimeters. So grab the calculator, and where there's an x, put a 32 in that spot for us. So nasty decimals. We rocked that last time, how nasty they were, but put a 32 in there. And we'll just write them all down. It's kind of, I think, is that what it was? You know, we'll just write them all down. So that's what the line would predict. Based on this value, they predicted that a person who has a 32 centimeter foot would be this. But the weird thing is, there actually is somebody that's got a foot length of 32 in the data set. So they ask us to find the residual. That means like how far they were off, like we did last time. It was either actual minus predicted or predicted minus actual. We're going to look at this first. Yep, it's actual minus predicted. So I don't care if you write all that down. I'm just going to refresh my memory. You can do it in your calculator. The actual value is 188, and the predicted value was this, and you need to subtract those from each other. So in my calculator, like I kind of already have that nasty decimal right there, but doesn't the 188 have to go first? So I could type 188, and then I don't know if you've ever seen this before or not, but you can, let me make this larger so you can actually see it real quick. You can actually subtract away that previous answer without punching it in. Right above the negative symbol, it says ANS. If you just hit second ANS, it will do that for you. Or you can just type 7.846 or whatever. But this is the residual, and you can jot that down. Was he positive or was he negative? Positive, because wasn't the actual bigger than the predicted, right? So we did that last time. That was the residuals, and that was pretty close, right? It was very, very close to what it predicted. You probably remember this back in the 90s. He was one heck of a basketball player, but he's still on TV. You ever heard of Shaquille O'Neal? Like, pretty famous dude. If you don't know him, that's fine. He's a big, tall man, right? He is a NBA center. He is pretty tall. His foot size is 38 centimeters. So let's use this formula right here to put 38 in there and see what his predicted height would be, right? So we'll go in there and do this. Go ahead. Yes, we're going to put 38 in instead of 32. Time 1 second. I put 32. Let me pause. Cool. That's a good question. So I got this guy right here, 207 points. I'll just call that 7. Is that okay? 207.7. Since they don't ask us to find a residual or anything like that, so I actually didn't write the whole thing down. That's okay. But to me, because we live in America, that is useless information because this says he is 207 centimeters tall, and I don't know how tall that is because I don't measure stuff in centimeters. So I went and figured 6'9". This you have to write this down. This equation predicted Shaq to be 6'9" tall. And then I looked it up. He's actually 7'1". That is a difference of 4 inches. Are you with me on that? Like they're off by 4 inches. Do you feel that this equation was accurate for Shaq? They said predict his height, and they're off by 4 inches. Interpolation is fitting the data well. Extrapolation means it does not fit the data very well. It's too far out. Too far out. So Shaq's an outlier in this situation. And we're just going to take a few minutes to kind of realize why. Is because how many people did they measure? How many total people did they gather? Like, that's not going to predict things well. You need hundreds of people to get good, accurate measurements to see like how foot size compares to this. Let's talk about the next concept of uploading an outlier in the data. So we got a table of all these candies. It says a scattered plot made below as well as the least squares regression line. Which candy seems to be an outlier? Look at all those dots. Pick a dot. Which one do you feel is the outlier? Probably that guy way up here. Are you with me? It doesn't fit the data very well. Can we find him in the chart of which candy he is? This is like how much sugar is in the candy versus how many calories it has. Cool. Which candy is it? Peanut M&Ms. Are we okay with that? The peanut M&Ms is probably the outlier in that situation. So here's the weird part. We'll get better at this as we do it. If you still aren't a little sure about it once the worksheet is over with, by the time you're done with the homework, I guarantee this will get easier. The more you do something, the easier. Where is this green dots compared to everybody else? Let's start with this. Left, right, or middle. Where is this dot? Is it way to the left, way to the right, or kind of in the middle of all the other dots? Yeah, you're not wrong about the little bit to the left, but what I mean is like way left, way right, or more in the middle. Middle. And then how about where is it in relation to the dots above it or below it? Not the line, the dots above. So that's where that guy was. He was to the middle and above it. And here's the weird part. Here's what an outlier does to the graph. It kind of is like a magnet. Imagine the outlier is a magnet. You see, this is the regression line right here, and it took the data and will change it. It goes straight up in that situation, like a magnet. If I asked you to find the average age in this room, am I an outlier? Am I a high outlier or a low outlier? Too high. Isn't it going to raise our average up in that situation? Cool. All right, let's try another one. So, oh my bad. How did the y-intercept change with the outlier? How did it change? Here's the y-intercept in green. Here was the original guy with the outlier. Here was it before. How did it change? I know what you mean by it went down. Like, that's what it would look like if we didn't have the outlier. So it actually went up. Because this is what it should be. This is what the outlier did. How did the slope change? I would say not much. The slope was like 2.8, and then it was 2.6. Not much. Let's try the backside and see how we do. This is what the homework questions look like. Here is a big cluster of data right here, and can you see that there is one dot that is just messing everybody up? So they have two lines graphed. This dude right here, I'm going to use a highlighter since I'm recording. This dude right here is like what the regression line would be if you didn't have the outlier. Are you okay with that? And this guy right here is the regression line if you did have the outlier. Watch my straight edge here. Sorry for the video people. But you see, this is where it should be. And if this is like a magnet trying to magnetize it, isn't it going to go boom? In that situation, it just sucked that line to go all the way up to there, where it totally changed the slope to go from positive to negative, and it did weird things to it. Why? Where is this dot in relation to the rest of them? Left, right, or middle? Very far to the left. So that is going to take this y-intercept, which is way over here, and move it up. Are you with me on that? It's going to totally make it go up in that situation, and it's going to change the slope. So because the outlier is to the left and above the data, that's why it's going to make it go up, because it was above the data. The outlier pulls the left side of the line up and increases the y-intercept. Thank you. Just set that on my desk right there, or that's fine. Because it was to the left and above, that outlier pulls the left side up and increases the y-intercept. And you'll have about 6 of those to go through on homework. Trial and error will get you to figure out how it works out the best. It's where is the outlier, to the left, to the right, to the middle, above or below, and it will be much easier than you think. But the last concept of the day, go ahead, it's called regression to the mean, and I have 3 quick examples. So you guys cool that mean means average? Are you with me on that? Check this example out, just talking out loud. Here's example 1. After 5 games played in the 2025 season, the Los Angeles Dodgers were 5-0. They play 162 games in a season. Do you think that they will go undefeated the rest of the year, or will it start to average out? What do you think? Will they go undefeated? Probably not. They will probably lose some games. Even though statistically they have never lost, they will probably average out. You can go back to Dakota. Example 2. A person who has ever rarely thrown darts has to throw 3 darts on the dartboard. First one they throw, bullseye. Do you think they're going to get a bullseye every time? They rarely throw darts. Do you think they're going to get a bullseye? Or maybe they're just not lucky. Could be complete luck or partial luck. But do you think they will start to average out that they won't get a bullseye every single time? They will regress to the mean, right? And then the last one, Steve has to guess if a flipped coin will be heads or tails, right? So heads or tails. He is asked to guess 100 times. So they're going to flip the coin 100 times. Heads or tails, heads or tails, heads or tails. You got to guess. First 4 times, he got 3 of them right. Isn't that a 75% success rate? Do you think it's going to continue, or will it start to average out to where he'll get probably half of them right and half of them wrong? Because isn't there a 50-50 shot on heads or tails? Are you with me on that? So just because you start strong or start really weak, it doesn't mean that you're going to stay that way. You will regress to the mean. Yes. So let's try it on a problem right here. Regression to the mean. These are kind of hard to understand. Somebody's taken the Somebody's taken the ACT 2 different times. On the x-axis, this is their first score. And on the y-axis, so I don't know if I cut that off, this is their first score. And on the y-axis, this is their second score. So imagine, I'm just going to put a little dot on here. You don't need to draw this dot, but this dot I put right here. I'm going to use a different color than blue so we can actually see him. Imagine I put this dot right here. Its ordered pair is 10, 20. Don't put that on your paper, though. You see, 10 is the x value, and 20 is the y value. What does x stand for? First score. First time they took the ACT, they got a 10 on it. What does y stand for? Second score. Second time they took the ACT, what did they get on it? 20. Are you cool with how to kind of read this? Just hold on. Hold questions, okay? What does this ordered pair mean right here? It is at 28, 20. What does the 28 mean? 28, which time? Which time? First time. What does the 20 mean? Second time. How did they do? Better or worse the second time? They did worse. Cool. What does this ordered pair mean right here? 18, 22. 18, 22. 18 the first time, 22 the, how did they do? Better or worse? Better. And here's a crazy one. What about this one right here? That's 13, 13. What did they get the first time? 13. What did they get the second time? How did they do? Better, worse, or the same? See, it's on the line y equals x, right? So like that means the first time equals the second time. So now that we kind of understand how that's read, check this out. It says how many students scored above 22 on their first try. So first try is the x-axis. Here's 22. It's all of these dots that are to the right of it. Hold on, I just totally hit the wrong button. Okay, so it's all of these guys to the right of it, where the x value is bigger than 22. Is this guy bigger than 22 for an x value? Just an x value, right? You see how I have this line right here in red? If it's bigger than 22 on the x, doesn't have to be on the right side of it in that situation. So let's count them up. 1, 2, 3, 4, 5, 6, 7 of those guys are totally to the right of that situation. So how many dots, how many people scored above 22 on the first try? 7. Give me a second, Ethan. I want to finish this, and then I'll answer your question. So 7. What percent of those students scored better on their second try? Here's what this line is all about. If you are above this line, in pink that I'm putting right here, you did better the second time. If you are below the line, you did worse the second time. How many of those 7 dots are above that pink line? 2 of them. 1, 2. Do you see those 2? Like they are above that line right there. This is score 23, like 25. Didn't they do better the second time, right? This is 25, 26. Didn't they do better the second time? Well, this one is 24, 18, or 17. They did worse the second time. Why are they worse the second time? Because they're below the line y equals x in that situation. So how many did better the second try? 2 out of 7. And we got to calculate that percent right there. So 2 divided by 7. They would like us to round to 1 decimal place on homework, so I like the 29%, but we'll do 1 decimal place. So how about 28.6%? Are we okay with that? So it's a weird one to read, but because they did better the second time, they're above that green line right there. That is the line y equals x. And just for fun, what would this mean right here? Did that person do better or worse the second time? Where are they at in relation to the green line, above it or below it? So they did worse, right? What does this score mean? Did they do better or worse the second time? Better. It's above the green line in this case. Did any student score the same both times? That one right there, yes. That one did, so that's a big fat yes.